So first, I'd like to thank the organizers for inviting me. It's a great honor to be part of this celebration. As you can tell from this slide, the focus of the talk will be of what we've learned from space geodesy about the process of strain buildup and release at plate boundaries. Space geodesy was not a technique available at the time of the plate tectonic revolution. Before I go into the science content, I'd like to say a few words about Paul Taponnier and how much I owe to him. Paul Taponnier has pioneered the use of satellite imagery and geomorphology to study active tectonics, and he's the one who attracted me to earth sciences. At the time when I was considering moving into mathematical economy, I did a recreational internship with him, and that changed my track in life. And then I decided to go for a recreational PhD with him in earth sciences, and 30 years later, I'm still in earth sciences. I'd like to thank also Vincent Courtillot, who I worked with at the time of my PhD. I did a little bit of paleomag with him. I stopped at drilling cores. I didn't go much further than that, but Vincent gave me important advices many times during my career. I was inspired to work on the seismic cycle on Megathrust by lectures that were given by Xavier Le Pichon in these institutions. I think it was around 91, 92, something like that. At the time I was starting working in the Himalaya. The other person I'd like to thank is Kerry C. Kerry C is the person who attracted me to Caltech and with whom I've had a very enjoyable and fruitful collaboration studying the Sunda Megathrust. Finally, I'd like to thank all the students on postdoc who did the hard work that I'm going to present today. And I'm not going to put all their pictures on that slide. That would be too many of them. So today it would not take much imagination to reinvent plate tectonics. Seismologists have done their part. In case you were wondering what they were doing at the time of the plate tectonic revolution, they were producing those dots that are actually defining the plate boundaries. And from space geodesy, you can measure today velocities at the surface of the Earth, and it's in your face that you have plates that are rigid and moving around the yellow pole at the surface of the Earth. So seismologists also contributed to a better understanding of subduction zone, the state of stress at subduction zone. Peter Molnar was talking about that yesterday. And defining also the structure of the lithosphere. And one thing that was demonstrated early on is that the seismologic depth, the depth range within which earthquakes can nucleate, is probably controlled by temperature. You see that very clearly in the oceanic lithosphere. The older the oceanic lithosphere, the deeper the intraplate earthquakes can reach. As a result of that, subduction zones are the place where the largest earthquakes are occurring on Earth. This is an effect of the low deep angle of the subduction interface, which I call a megathrust, a thrust, a crustal scale, lithospheric scale thrust. And it's an effect of cooling of the plate interface by the advection of heat downward. So, as a result, subduction zones are producing the largest earthquake on Earth. 90% of the global moment release over the last century was released at megathrust. And actually, if we were redoing that calculation today, I think it would be higher than 90% due to the flurry of large megathrust earthquakes we've had over the last 10 years. So, the process, in the early days of plate tectonics, there was high hope that we might be able to soon predict earthquake, or at least assess seismic hazard better. The idea was simply that once you have demonstrated that most of the strain at the surface of the Earth is occurring on localized plate boundaries, including subduction zones, And once you recognize this and assume that a particular plate boundary will produce always similar earthquakes, you come up with this simple view that you should have long period of locking of the plate interface during which stress is building up and sudden episodic slip event, earthquakes releasing the accumulated strain. So at the time, people thought that, okay, now that we know about the plate boundaries, where they are, we know about the velocities along those faults, we should be able to determine where earthquake might happen and how frequently they might happen. So one hypothesis that was put forward early on is the seismic gap hypothesis. If you know when was the large earthquakes, in a simple model of strain buildup and release like that, you should be able to tell when the next will be. And if a particular area has been quiet for a longer time, it should be a place of higher probability of a future large earthquake. This hypothesis has failed spectacularly, I must say, and most of the seismic gaps that were identified 50 years ago are still standing. So this is an issue that we now understand better thanks to space geodesy, as I'm going to show in a few slides. We are better off today assuming a Poisson process, assuming that the probability of an earthquake is actually independent of time. Another hypothesis that was put forward is that if you multiply by 2, let's say on this plot, you have strain built up in the interseismic period, strain released during an earthquake. If you multiply by 2 the slip rate on the fault and assume that the plate interface ruptures with the same earthquake, you're going to multiply by 2 the rate of earthquake. So the seismicity rate should scale with the fault slip rate. And this hypothesis actually holds, and it's a tool that we're going to use in what I will present today. The last hypothesis, the maximum, the notion that the maximum magnitude at a plate boundary should depend on the age of the subducting plate and on the convergence rate, was a very appealing hypothesis. But this one has failed quite spectacularly as well. This is a proposed correlation that was produced 30 years ago by Roof and Canary, where they were plotting the data available at the time. And what they were proposing is that magnitude 9 earthquakes would happen where you have either a large convergence rate or a very young seafloor age. Now, if you populate this plot with all the earthquakes we've had recently of magnitude 8.5 or larger, they are all over the place. So actually, we don't understand very well how the maximum magnitude earthquake at a megathrust relate to the convergence rate or the seafloor age. But as we will see, we can address this question with space geodesy now. For those of you who might not be familiar with basic notion in earthquake science, actually including my sister or my brother-in-law who are sitting in the audience today, I'd like to introduce a few notions. First, the seismic moment. The seismic moment is the integral of slip on the fault area. And it's a basic quantity that you can determine from seismological waveforms. The moment magnitude is simply a logarithmic scale based on the moment magnitude. Another basic notion that will come across the talk is the Gutenberg-Richter law, which is an empirical observation that was made quite early on by Gutenberg and Richter. This law states that if you plot the log of the number of earthquakes above a particular magnitude, you find that it decreases linearly with the magnitude. Okay? And the slope of that curve is called the b-value, which is generally of the order of 1. So it says that if you do it globally, you have about 1 magnitude 8 earthquake every year globally, but you have about 10 magnitude 7 earthquakes over 1 year. Okay. So this law holds globally, but it holds also locally. And even in the lab, if you do experiment on a rock sample, you would find this law. Another notion that will come across the talk is the empirical observation that the moment of an earthquake scales, the moment is here, scales with the area of the rupture to the power 3/2. And this is actually the scaling that you expect with a very simple model. If you have constant stress drop on a circular crack, you would find that the stress drop scales with the shear modulus multiplied by the slip divided by a length scale characteristic of the fault, so the square root of the area, and you introduce the definition of the moment, and you find this scaling law. So what it tells you is that most earthquakes have a stress drop of around 3 megapascal. Another notion is the conservation moment principle. So let's assume that the white area here is the seismologic zone, the zone that is going to rupture during earthquakes. Even if those earthquakes are very different from one time to the other, you can sum the moment released by the earthquake, and you can divide the moment by the area, the shear modulus, and by the time over which these earthquakes have happened. And that will give you the seismic slip, the average slip that has resulted from all these earthquakes on that area. So now if that white area only slipped during large earthquakes, what you would find is that this, on the long-term average, if you have a catalog of earthquakes that is long enough, the velocity that you get from this should match the long-term velocity on the fault. If you have independently a measurement of the long-term velocity on the fault, V, you can take the ratio over Vs over V, and that determines the seismic coupling, which is a quantity that was quite popular earlier. So people have calculated the seismic moment coupling at a number of plate boundaries using velocities derived from global plate models and using seismicity catalog. And here I'm using a plot from Froelich and Wetzel, who found that at subduction zone, the coupling is highly variable, but is on the average of 0.6. So 0.6 is significantly smaller than 1, which suggests that some fraction of slip within that white patch that is the seismic zone is probably a seismic. However, there's a lot of scatter on this plot. The seismic coupling is on this side, and this is a logarithmic scale. It varies a lot. And the reason it varies a lot is that you never have a catalog of seismicity long enough to represent the long-term average. So this quantity, the seismic coupling quantity, is very difficult to make use of. From space geodesy, you can estimate this quantity differently, and we're going to call it the interseismic coupling. And it is based on the idea that if the plate interface is locked in the interseismic period, the upper plate is going to be compressed as the lower plate is subducting, and it's going to be compressed, producing geodetic strain, and it's going to be dragged down as well. So if you measure the deformation at the surface, represented by those curves with GPS geodesy, you can invert for the extent of the fault that is locked in the interseismic period. And if all that happens is episodic slip on the plate interface during earthquakes, the interseismic coupling, which is going to be the deficit of slip in the interseismic period divided by the long-term slip rate, should be equal to the seismic coupling. It should be the same quantity. It's not exactly the same because there is also the contribution of seismic transients. We'll come to that later on. So people have been using now for quite some time this approach to determine the pattern of locking of plate interface. And something that is quite clear now is that some gaps, like this one, which is along the South America subduction zone. So we are at the border between Ecuador and Chile, and on Peru, sorry. And what you see here, no, it's Chile, sorry. And what you see here is a long gap. This is Peru, Ecuador. You see a large gap that hasn't produced any earthquake for a long period of time. Mohamed Chli and Jean-Mathieu Noquet and colleagues have been collecting GPS measurement in that seismic gap. And what they observed is this. These are the velocities relative to South America. And what you see is that in the south, where you've had large earthquakes, the upper plate is compressed, so indicating coupling of the plate interface. But in the area where you have the gap, there is very little strain of the upper plate. So basically, the seismic gap is a zone of aseismic creep along the plate interface. So many of the seismic gaps that were considered to be area of high seismic hazard actually are area of low seismic hazard because they're creeping aseismically in the interseismic period. So that explains to some degree why this first hypothesis, the seismic gap hypothesis, has failed so spectacularly. Now I'm going to talk about the Sumatra megathrust because this is one place where you can describe the seismic cycle, the pattern of strain, accumulation, and release during over the long term, using both GPS, but also a technique that Kerisi has been using a lot in his group, which is based on studying coral reefs which are fringing the islands of the coast of Sumatra, and which have been recording the pattern of subsidence and emergence of those islands as the result of the seismic cycle. So let's talk first about GPS geodesy. So here, these are velocities measured from GPS relative to Australia. So you see, for example, that in that area, those arrows about the same length as those ones. So there is very little strain here. So the coupling here on the plate interface should be small. You move north in the area of the Mentawai Islands, what you see is that those arrows are much larger than those arrows. So there is compression of the upper plate, which is an indication that here the plate interface is locked. So if you use the principle I introduced earlier and determine the pattern of locking of the plate interface, this is what you get. Dark red is where the place, where the plate interface is locked, and where it's white, the plate interface is creeping at the long-term slip right along the fault. So in the south, there is very little coupling. In the Mentawai Island, there is high coupling. Same thing during beneath the Nias Island. So now you can compare this pattern of coupling with the rupture area of the large earthquakes which occur offshore Sumatra over the last 10 years. And so starting with the Nias earthquake of 2005, and you find that the rupture area of that earthquake coincides quite well with the area of the plate interface that was locked before the earthquake. So it shows somehow the predictive power of this coupling map in terms of the location of possible earthquake. For the south, we see that the 2007 Bengkulu earthquake ruptured actually only a fraction of the area that was locked there. So it shows more complexity than what we have in the north. And there was another large earthquake 12 hours later, which ruptured the same area, but not entirely. So this area has yet to rupture offshore Padang, and it hasn't ruptured yet, but it could happen anytime, probably. Another thing that we discovered with space geodesy in that area is that those earthquakes, so the Nias earthquake here and the Bengkulu earthquake, were followed by a lot of post-seismic deformation, which can be modeled quite well as creep on the plate interface, either up deep of the rupture or down deep of the rupture. Up deep of the Nias rupture here, down deep of the Nias earthquake, which shows that that area that is locked, that seems, that a fraction of that seismologic zone can actually probably creep during transient event triggered by large megathrust earthquake, something that we have to take into account. So What we've learned from from studying the Sumatra subduction zone is that the pattern of coupling of the plate interface is very heterogeneous. Ruptures tend to be confined in areas that are locked in the interseismic period. And then you have afterslip that can contribute to release strain on the plate interface. In Sumatra, it's possible also to describe the seismic cycle over the longer time scale using coral data, as I mentioned earlier. So this is a picture of an island that was uplifted after the Nias earthquake. And what you see, this is the coastline of the island before the earthquake. This is the lagoon, this is the coral reef. The entire lagoon on the coral reef was emerged during the earthquake. So the technique that Kerry and this group has been exploiting is that you can use these coral heads, which are actually growing at a very shallow depth of maybe 10 centimeters or so in pancake shape. And these coral reefs actually are recording the relative motion of the ground relative to the sea level. So, for example, a coral head like that, which has a funnel shape, indicate that the sea level was rising as the coral was growing laterally. So this is a place where the island was subsiding, was being dragged down by the plate interface. And it's been emerged during the Nias earthquake, and the earthquake then died. And so when you date the outer fringe of this coral head, you can date the earthquake. If you look at the shape here, which is represented here, you can get how fast the island was subsiding before the earthquake. So now if you collect many coral heads like that at different elevation, you can piecewise describe the pattern of subsidence of the islands in the interseismic period and uplift during coseismic events. And so we've been using these measurements from many coral heads at many sites on offshore Sumatra in the Mentawai Islands area. And using this data, we have produced a time-dependent model of coupling of the plate interface. So this is what is represented here. So where it gets blue, it indicates that the plate interface is locked. The islands are going down. They are dragged down by the subducting plate. And when it turns red, like here, you have an earthquake. Okay? So using this technique, you can describe now the process of strain buildup and accumulation over centuries. So extending what you can do with regular geodesy. So to first order, when you look at the result of this modeling, to first order, the pattern of interseismic coupling is relatively stationary. It's not exactly stationary. It varies a little bit, but not a lot. And this is why you find a correlation between coupling map derived from space geodesy today with the rupture area. If it were changing all the time, there would be no correlation. Now, if you look at the ruptures during the earthquakes, they are highly variable. So these are the rupture area of all the earthquakes. So there's a complexity in the system. You're not producing always the same earthquake. So how can we explain this complexity? Why is it that a locked patch would produce sometimes a rupture to the south, sometimes to the north, sometimes it would rupture the entire locked area? A simple idea is that the plate interface is paved with area that would be what we say rate weakening, where earthquake can nucleate, and area that are rate strengthening in gray here, where slip can only be a seismic. And it can be transient slip, like after slip, or it can be regular, steady seismic creep in the interseismic period. So the idea is that if you have a system like that, what you measure from space geodesy in the interseismic period is the coupling effect of all the spins. You might see that as spins spinning the plate interface. So where they are packed together is going to pin completely the interface, and you would see a wide area that is locked. And when the earthquake happened, the earthquake would rupture a fraction of those rate weakening areas, a fraction of those pins would break, and immediately after the earthquake happened, it's going to shade high stresses on the area around it, and then you will see those intervening rate strengthening areas producing aftersleep. So, in principle, if you can describe the seismic cycle over a long enough period to get interseismic coupling, rupture area, aftersleep, you should be able to image those spin and produce a deterministic model of the seismic cycle. We never have the data to do that, unfortunately. Here is a simple dynamic modeling of the seismic cycle that explains what kind of complexity can arise when you have simply two patches that are rate weakening. So in this model, we have two patches within which earthquakes can happen. So they are represented by those two rectangles. So in this model, in the interseismic period, those areas are locked, and what is plotted here is the log of the slip velocity. So where it's black, it's locked. And the rate of the movie is slowing down during earthquakes so that you can see the earthquake happening. So you have long periods of interseismic locking, so of strain buildup, and sudden slip event that we've just seen. And when you have these two patches close together, sometimes they're going to break together, sometimes they will break independently. So you have this kind of complexity that we see in the data from Sumatra. So the dream would be to use such models and calibrate the model based on observation, geodetic observation, seismological observation, to produce a dynamic model of the seismic cycle in which you would be able to assimilate data, and then you would be able to estimate seismic hazard based on reasonable physics. We are not quite there at the moment, but something that we can do is use the moment conservation principle, which as I have introduced earlier, and which is built in those dynamic models. So here we have the plate interface, and we assume that it's going to rupture during large and small earthquakes. So without going into the detail of that, you can actually determine what is the end point of the Gutenberg-Richter distribution resulting for all these earthquakes, so that the moment released collectively by all those earthquakes and also by afterslip produced after this earthquake is going to balance the moment deficit during due to locking of the plate interface in the interseismic period. So from geodesy, you get this blue line. You get the location of the endpoint of the Gutenberg-Richter distribution. From seismology, you get the distribution of earthquakes. You get the red lines. So in principle, if you have seismology to give you the red lines on the blue line, you can determine what is the model of seismicity that would balance the moment budget. And in particular, you can extrapolate to get the maximum magnitude, its probability of the PDF on the moment and the PDF on the return period of that earthquake. And this alleviates the problem that the seismicity catalog is too short to get the large earthquakes well represented in the catalog. But the small earthquakes are well represented. So this is the technique we've been using. So if you do that in Sumatra, these red dots are showing the Gutenberg-Richter distribution from the seismicity catalog. The blue line is showing where the distribution should end so that there is a balance between moment release and moment deficit in the interseismic period. And when you plot the data from the historical catalog and the paleogeodetic data, you find that there's a very good match. Now we can do that because we have the information about these large earthquakes. If you use only the data before the earthquake, that's what you would have had. The triangles are showing the Gutenberg-Richter distribution due to the seismicity recorded before 2007, before 2006, before the 9th earthquake. And what you find is that in that case, the extrapolation is more difficult because you're missing the large earthquakes, and more importantly, you're missing the aftershocks on the afterslip related from due to these earthquakes. So you cannot simply extrapolate this data. You need to include them in the distribution and include their aftershocks. So we designed a a procedure to do that with Vicky Stevens. And when we apply it to Sumatra, this is what, and using the data before the Sumatra Denias earthquake, so the blue line is showing those data. You apply this technique, and this is the PDF here of the location of the maximum earthquake that you get. So this shows that if you have geodetic data to tell you where to end the Gutenberg-Richter distribution, seismicity data, you can make reasonable estimate of the return period and the magnitude of the largest earthquake at the subduction zone. So, and maybe I should end soon. So I'm showing now what the result we got applying this technique on Tokuoki area. So when you take this approach, what you find is that given the pattern of locking that can be calculated based on the geodetic data available before Tokuoki, you get that the endpoint of Gutenberg-Richter distribution in Sumatra should be along this blue line. You applied the technique that I described, starting from the seismicity catalog before Tokuoki, the blue line here, and you end up with the need for magnitude 9 earthquakes or larger with a return period of 500 years. Yeah, so I hope I convinced you that there is value in using space geodesy on the other technique to describe the pattern of strain accumulation and release to evaluate the probability of large earthquakes. And I think we've made progress in terms of using plate tectonics, combination with space geodesy, to assess seismic hazard at plate boundaries. Yeah, thank you for your attention.